famous.
Man, it's 3,000 emails a day, mate. Really just wanted to wait. You just appear in the mountains. No, well, yeah, cool. So scalable matmul-free language modeling. I'm catfishing you a little bit here because I'm going to break it down a little bit into, I suppose, the history of what went into developing it. I don't even know this. Yeah, it's what am I going to talk about? I'm going to give you a 5-minute primer because I realized I don't think there's been any ground level 101 spiking neural net tutorials. So I'll keep it real succinct and real basic. I'll talk about how we scaled up spiking neural nets to do language modeling with Spike GPT. Following that, I'm going to tell you all the things that are wrong with Spike GPT and what led us into just building something else and going down the pathway of more recurrent language models, models that are evolving over time. And finally, we'll hit the technical details of the matmul-free language model that we've developed. So without further ado, SNF, let's go. Why do we care about spikes? Hands up if you don't know why the big deal. Excellent. Andreas. Neither do I, to be honest. But the story goes something like this. Biological neurons interact via single-bit spikes in order to address difficulties in long-range communication. And if you really want to port that over to deep learning, then you can take your activation and treat it as a 0-1 spike. You have a 0 times a weight, that's a 0. If you have a spike or a 1, multiplied by a weight, that's just the same weight itself. So the idea is if you have enough sparsity in your spiking neurons, then you can hopefully skip a lot of your memory accesses. Great. Sparsity. Now, biological neurons are going to spend most of their time at rest, setting most activations to 0. So, a very toy example I like to give is, I've got a list of numbers. I could read it out to you and say 0, 0, 0, blah, 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 7, blah, 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 5. That's very inefficient. Alternatively, I could condense it down in a run length encoding type of spirit and say 7 at position 10, 5 at position 20. Right? So if you have to cache a bunch of activations, so we're not necessarily talking about weight or memory access, but if I have a very large model, a matrix multiplication, and I need to cache some of those values, if a lot of them are 0, then maybe it just makes sense to only increase my memory usage with additional non-zero elements. Cool. Then static suppression, that's just me being very contrived to trying to get rid of this out there. There are many catches to all of this. This is why
It's very easy. Yeah, you actually put it up with these because now you need a fancy way to read out. But you just don't.
Now you need a fancy way to read out. So of course, everything with sparsity adds a bit of overhead. And if you're not going to be able to exploit that sparsity, you're going to run into problems. So that is to say, a lot of this is, I wouldn't even say opinionated, right? It's only going to be useful to you in very specific circumstances. So you're not going to get benefits from spikes just because they're spikes, right? It's something that really should be clear. Now, event-driven processing, sensory periphery only processes information when there is new information to process. Not like completely true, but you can take advantage of this idea that humans are only really paying attention to dynamic information. You've probably stopped paying attention to the exit sign over there, for example. Rather, you're looking at me, waving my head, etc. So we've looked enough at event cameras today, so I don't think I need to really convince you about where to go from there. So if we want to do computation with spiking neuron models, one of the more common ones is the leaky integrated fire neuron. Let's just get a qualitative feel of what this bad boy does. If this neuron is sufficiently excited over time with enough input current injection, then it's going to trigger its own spike to downstream neurons. In absence of that excitation, it's completely quiet. You can think of it as 0 activations. How does that work? So let's open up that neuron body. So surrounding that thin film insulating membrane, on the outside you have a bunch of ions. On the inside you have a bunch of ions. So what do we have? Ions are just in an aqueous medium, a conductor, right? So you've got conductor, insulated conductor. Circuits 101, what is that? That's a very shy capacitor. So you've got a capacitor, you can integrate charge on it when you apply some input current. By the same token, you've also got little ion channels that let ions pass through to achieve some sort of equilibrium looking thing. So very crudely, while it is a highly dynamic system, we can just say fuck it and go ahead and say that's a resistor, right? You've got capacitor, you've got a resistor, you've got a first order low pass filter. Great. So the idea is this: neuroscientists stole from electrical engineers, so it's time to steal their models back to hopefully make our things a little bit more efficient. if there's no, if you have a shaky circuits background, don't worry. Very qualitatively again, let's say that I apply some input current into this leaky integrated fine neuron. What do I get? I get some charge integration, and over time it's going to leak. It's going to exponentially relax back to a steady state value. What's represented here is the membrane potential across that capacitance from the extracellular to the intracellular medium. Cool. So this charge leakage is occurring because of the resistance from the ion channels. That is what introduces the leaky and leaky integrated fire. Now, if I was to apply a current train, then we see these kind of jumps riding on top of one another, right? That's your integrate. What about the fire? So if I introduce some arbitrary threshold into this model, in this case, it's a hard threshold, which is not necessarily how biology works. But if that membrane potential hits that threshold, then it triggers a spike to all downstream neurons and things start to get computed. And in the spirit of introducing some sort of refractory period, we're also going to add some reset mechanisms just to clamp that membrane potential back to zero. Cool. Any questions? No. Awesome. Yeah. Good. Yes. No, if you do want to get into lower level deets of spiking neurons or whatever,
is your paragraphs, in your paragraphs, the equations don't have the right dimensions.
No, so they've done, and I can explain that to you in this little bottom note. 1 minus b is removed because in the context of deep learning, who cares? It still works. And if you want to model something appropriately, then sure, keep the dimensions correct. And I mention every time I mess around with my dimensionality when I break that rule, because ultimately deep learning doesn't seem to care about that sort of precision. Now, if I want to take that continuous time dynamic, then you can solve it using favorite numerical integration method. Forward Euler is a popular one because it's simplicity and how it easily maps to a recurrent neuron. And I can just say, all right, my current injection is represented using x discretized over time, scaled by some weight w. That gets added to the membrane potential of the neuron body, which is going to accumulate charge. And if that exceeds a threshold, then it triggers a spike S. And at the same time, it's going to kind of route back. Your previous membrane potential is going to route back around. It's going to be scaled by some decay factor beta. So beta is between 0 and 1. So that's how you get that exponential decay. So if beta was 0.5, you're just going to keep halving your membrane potential as subsequent steps. It's all well and good. Then in terms of equations, the spiking dynamics are just represented by some shifted heaviside function, right? If you're greater than your threshold, if your membrane potential exceeds your threshold, you generate a spike. If it's below the threshold, you do not do anything. And if you want to do some training, it makes more sense to unroll this, to express this explicitly and unroll it over time. So this here is what is just one neuron. We're moving forward in time from left to right. And it's just the exact same thing right there. Now, if I want some lighter parameters in, then my current can be represented using the product of x and w. So this w is shared across time. And now that we have this acyclic computational graph, which is all the neural networks are, the leaky integrated fine neuron is now compatible with all of the tricks and hacks that go with training deep learning models. All well and good. Of course, you run into some non-differentiability issues, and so what the community generally does to address that is to apply your heaviside operator on the forward pass to induce some sort of sparsity. Go backward pass, they just smooth it out. We know that works. The quantization aware training and binarized neural network literature kind of showed us that using straight-through estimators, and this is no different here. So with that being said, let's take a look at what one layer of spiking neurons looks like. That's just one neuron. Let's scale it up a little bit to the one layer. So we've got a bunch of inputs, much the same way. I think I'm being a little inconsistent with notation. So my decay rate is now represented using this recurrent weight matrix W. Andreas?
Just to calibrate something, in a physical instantiation or a model, you still have a simple neuron, but what you've shown us before is a tree that allows you to train this like that.
Yes, exactly. So the way that you would train a recurrent neural network is by unrolling the graph. And then you can back propagate through all of these forward connections. I'll show you a visualization later. So this is now 3 different neurons here, all well and good. At say t equals 1, at my first time step, I'm going to take this is now my hidden state, denoted by the very inconsistent with notation. Forgive me, I finished the slide like an hour or two ago. We've got my hidden state at t equals 1. It's going to be scaled by that. It's going to be equivalent to some diagonal matrix of recurrent weights multiplied by my previous hidden state. And that's going to be added to whatever input coming in. So x, we now assume that x has already been linearly weighted in the previous layer. And that's kind of interesting, right? So we get the membrane potential at the next step of 1 neuron using this, I guess, just vector matrix multiplication. And we get V2, we get V3, it's all well and good. And we get, we can alternatively represent that using a simple Hadamard product, right? That's, these zeros are just nulling out everything else. So you may as well just do some element-wise operation.
And W's are not a function of time.
W's here are not a function of time.
But if they are a function of time,
yeah,
and you can come up with a very efficient implementation of a neuron, let's say 1 transistor, would you actually think about, instead of building a kind of neural network and then worrying about when you're going to put the W's of building the right that, actually build literally embroider the hardware, build that as hardware.
Well, right. Are you asking if your W varies over time, would you just parallelize it and build it in that form? Ask me that question again at the end.
Okay.
Yeah, that's interesting because we're going to talk about parallel trading in a bit.
Okay.
Right. So this is just a Hadamard product. Cool. Plus the input. So how does this differ? So now we're going to go from t equals 1. We'll step forward in time. I'm just going to take the new output that I got, loop it back in here in order to update the hidden state, the membrane potential, the thing that moved upwards and then exponentially relaxed. So you just keep solving this equation and then you get the whole trajectory of the membrane potential. The next step, t equals 2, we're just going to update the subscripts to +1 and then t equals 3. You just keep doing this forever. How does that differ from recurrent neural networks in their original formulation? So we again start off with these 3 neurons and we'll project all of the membrane potentials of hidden states more generally into some dense layer. That dense layer goes through a nonlinearity and that is fed back and element-wise added into the input stimulus. So you can kind of tell that there's a bit of a difference here, right? So if your equation is now going to be a dense matrix, it's not diagonalized, it's dense. So all of the operations have to take place, right? And not just that, but we also have this nonlinearity. That may be a ReLU, it could be tanh. Those are probably your more common methods. What do we do now? We're going to compare recurrent neural networks in their OG formulation against spiking neural networks, right?
So where did the nonlinearity go here?
Where did the nonlinearity go where?
I mean, in our nonlinearity.
In your spiking neural network, your nonlinearity is spatial, so your spike generation is your nonlinearity, but we do not have a nonlinearity through time until you wait 30 seconds for an extra animation. Mark,
it's spiking that W is the factor.
Yes, and so previously I referred to it as beta. I'm going to be interchangeable.
Okay,
Yeah, so the W weight factors are going to be your recurrent weight matrix. I have hidden all your spatial linear connections in these pictures and just assume that X has already been linearly weighted. Good. So what are our differences? So in RNNs, I like to call it all-to-all recurrence because all of your membrane potentials are being mixed and they're being projected back into all of your recurrent neurons, and you have nonlinearity through time, right? Before you project your membrane potential, your hidden state, to the next step, you're applying a nonlinearity, right? In that sigma-like function. In spiking neural networks, you have one-to-one recurrence, right? One neuron, the hidden state of one neuron does not touch or talk to the hidden state of another neuron. And it's linear through time, right? This is linear. There's no nonlinearity applied to my hidden state. There is a nonlinearity applied when you go through to generate a spike. But you know what? I'm kind of lying to you, right? Because in order to introduce the refractory period, and this goes to Andres' question, you're going to subtract some value. Here I've denoted S to be the spiking output of my neuron, and that is nonlinear. Because in order to generate that S, I have to apply a Heaviside operator to the hidden state, right? And I'm kind of feeding that back into the state equation. So it does become nonlinear through time once we account for a reset mechanism. Keep that in the back of your mind. It's going to come back to all this a few times. So pain points of spiking neural networks. From a software abstraction, it's nonlinear through time due to reset. And I'll give you a better sense of intuition on why that matters. If it's linear through time, you can train that whole thing in parallel. I think it's like log n complexity. You get that. And secondly, you might argue that it has weaker representational capacity, meaning I've got 3 weights. The conventional RNN has 9 weights. It's 3 by 3. It's dense. So just intuitively, there's less to learn in this case. So maybe it can't represent as much.
But this is really big because of the square.
Sorry?
It's square. We really, the benefit is one is linear, the other is quadratic.
Yes. Hey, let's get going. And there's a lot more to say. There's a lot more to say. Now, in terms of hardware, I think that a lot of the people that have been around spike neural nets for a while can agree that the computation benefits of spikes don't really matter. It's communication. I mean, we care about communication. So sparksifying your activations and your data flow is really what we care about. But the moment you kind of go down to a 0-1 representation, you've lost a lot of information. And so maybe it's not something we want to do. Maybe we don't want to binarize activations. Rather, we want to perhaps just keep them sparse. Maybe. Again, this is all in the context of deep learning. I'm not talking about any sort of comp neuromodeling.
Just like, just a question. German big factors with synaptic connections. So is vector both?
I'm not sure. I don't care about fairness, to be honest. Like I'm just saying, what are the fundamental differences between RNNs and SNNs, right?
It's because you can have a explicit recurrent connection in spiking neural nets.
You can have explicit recurrent connections in spiking neural nets. I'm not going there. Yeah, I have a lot of opinions on them, but we can talk about that later. I'm just trying to be as so you can have explicit recurrent connections in spiking neural nets where you take your spike and route it back to the input of your neuron. Yeah, that's a whole conversation in itself. I could also say that the reset mechanism is another form of explicit recurrence. But yeah, let's get back to that. There's a lot to say in a short amount of time. Another potential challenge in hardware is that I mentioned this yesterday, 2 days ago, sorry. With SNN hardware, you're transmitting packets, right? You're not going to transmit 0 activation, right? If you don't have a spike, you don't transmit anything, right? And as a result of that, you don't know when a spike's going to occur. You can't necessarily speculate what's going to happen in advance. On the other hand, with recurrent networks, you have a fixed activation matrix all the time. You know what resources you need at every step, every sequence step of your operation, right? So you can take advantage of that. You can speculate, you can allocate resources effectively. And so this is a challenge. It's difficult to design around. And finally, asynchronous design, that's your weapon of choice for SNNs. It's just really fucking hard.
So you basically, you cannot
speculative execution. I don't think it's much of a thing in the SNN literature. Yeah. So the importance of linear recurrence, I think this kind of goes towards what you were saying. If you want to unroll everything, and can you just map that onto hardware? Now let's go through this by expanding the number of inputs to this neuron, and let's say that I apply a sequence of input spikes from x0, x1, x2 at different points in time. So x1 is going to inject something first, x0 second, x2. But what's that going to do to my membrane potential? Something arbitrarily like it's cool. That can be broken down again if you're comfortable with me being dimensionless and being inconsistent with that, then this is what that's going to look like. You have a decay rate multiplied by your membrane potential, plus the summation of your inputs over time and over neurons. These neurons are just firing independently of one another, though, so we don't care too much about that. Sequential computation makes training untenably slow. I'm going to visualize that for you here, by showing you what backprop for time looks like. But before we go there, an alternative way to do this, instead of having to sequentially update your neuron step by step, and you're relying on the previous hidden state in order to update your next hidden state, you can pre-compute a kernel, which I've just represented here as epsilon to follow the Slayer notation. And what I can do is just use that. I can scale it. I can introduce it into my membrane potential trajectory every time there's an input spike, and I can scale it by the amplitude of that input spike as well. So what that looks like is, this is very crude. I'm giving it a very crude treatment, but I just want you to get a sense of how to do these things in parallel. So if I already know all of my membrane potential responses are just going to jump up and then exponentially relax, I can pre-compute that and then just stretch it on the Y, on the X-axis on an as-needed basis in a way. So what's the membrane potential? Purely in response to the X0 spike, something like that. How about in response to the X1 spike, and what about X2? And then what you can do, you can compute all of these in parallel, sum them all together, instead of having to do things sequentially, step by step.
So you're showing some time invariance here.
I'm
Scale.
Yes, there are ways to get around that as well. Now, everything I've described ignores that reset mechanism. It ignores the key is it's just the non-linearity. The reset mechanism, I'm making a big point in that because this is going to move forward and explain what we did in matmul-free.
That's it.
Yes.
So this is not real time. You have to be cache your things that you already have.
Yes. Yep.
Yes.
So I mean, I've given you
It's not.
it's non-causal. Yep. It's not in real time.
So it's a hash map.
Sure. You could also do this using the parallel stat algorithm. Log it complexity that.
So yeah. So if you wanted to do real time, let's say you sequential processing, that's not cool.
No, if you want to do real time, then you're stuck with sequences. Yeah. If you want to do real time training, then yeah, you've got to look towards RTRL and various other forward moving learning algorithms. I'm staying away from that because we're not constrained in real time processing, and it's not good when you don't have that constraint. Nonlinearity breaks parallelism. This top picture doesn't know when there's going to be a spike. When there is going to be a spike, my final membrane potential gets clamped down. And so I don't know that there's a spike there. I don't know that this is going to be the membrane potential trajectory if I introduce a reset mechanism, or more generally, a nonlinearity. So with that kind of having been said, let's see how we scaled that shit up into spiking language models, especially some of the things that were wrong with it. But yeah, so Spike GPT, we built it something like I think a year and a half ago now. At the time, it was the largest Spike neural net trained by a backprop in the first full language generation. We did 3 variants and a very quick performance sample. Like it's, I don't know, it makes sense-ish, but it's a little bit weird. So I don't know, if this came out before ChatGPT, you'd be very impressed. Now, very boring. But what's good about this? Like, how did we approach this problem? So we built up upon the raw truth model, which in of itself is kind of considered to be sort of continuous time canonical system that's ultimately discretized. The weights are changed over time. Data is fed sequentially, much like how humans perceive the world. So you may know self-attention is taking entire sentences and sequences all in one hit, which isn't really how we do it, right? We were parsing things, as Kwesi mentioned, in real time, right? So this kind of goes in that direction, at least. And so we know that modern language models are not really dynamic. They require all of their inputs to be available in parallel. Now, state-space models and recurring linear recurrence is changing that. So that's kind of where we're going. And as a result, we got 30x less operations than a transformer of equal size. Well, of course, where we're running into a lot of problems, because if I try and scale this up from 260 million parameters, so for context, the estimate of ChatGPT to GPT-4's size is what? It's like over 1 trillion parameters, right? That's almost 1 trillion. All right, we got the CEO of OpenAI over there. 260 million is just like a little bit small. So if I try to take it up to 1 billion parameters, the improvement that I get from 260 million to 1 billion, and we tried it, was very incremental to the point where we were like, we spent a fair bit of money on those experiments on those GPUs to get very little out of it. And so after publishing this, we kind of realized that this in its native form might not be the best way to go about it. It seems like binarized activations are just really hard to work with. Maybe we go to ternary, maybe there's other ways about it. Maybe you induce sparsity from, say, top K activations or something. I don't know, but this wasn't quite it.
And it is.
Yeah. You guys can fight over the most.
So the spiking part in this was after the matrix look like
Yeah, okay, yeah. So I haven't gone into the detail because it doesn't work. So I don't want to waste time on things that don't scale very well. But yeah, the spiking part was before every single dense operation, which carries the largest amount of, I guess, compute complexity. That's where we had spikes with the argument that Hadamard products, their complexity scales with the number of neurons, whereas matrix more like n squared. And so that's where you want sparsity. That's where you want spikes.
Whether we drop out,
dropping out individual neurons, that's what you want to with recurrence, which is a cycling neuron, right?
So
You want that.
is dropping out while in the training process, is that predictable? Where it will not drop out?
So Andreas asked, is it predictable where you're going to drop out? I don't think so. I haven't really analyzed it. My feeling is that it's not. Maybe you could attach some regularization or some priors to force.
Because I think there is is because a lot of the progress is recently training large models is actually being able to predict where it's how the play will drop out.
Yeah, and I mean, if we could somehow adopt that into SNNs, which I don't think has been done before, like if you can induce some sort of speculative execution on this,
Yes.
that'd be pretty fucking fancy, I think. So
Yeah, that's really how the state of the art and that's where.
yeah, we don't want to be doing SNNs for the sake of doing SNN. We want to be competing and going further beyond what state-of-the-art deep learning does in particular problems, right? So why is the world using them? Scaling out. So how do we scale up? How do we keep pushing this forward? Let's look at recurrent language forms a little bit more generally than how I presented it to you. So let's say that we have this input sentence. I probably love you too much. Andreas or Toby with binoculars, right? Who has the binoculars? Is it Andreas that has the binoculars, or is it Toby that can have the binoculars? The sentence is ambiguous by design, right? So what self-attention is going to do is going to take the same sentence and it's going to find the correlation and the importance of one word against every other word. Let's just give a toy example here and say that Andreas and binoculars is really lit up. It's really red down here, right? A very high number in that self-attention matrix. But then the Toby and the binoculars is a bit weaker, right? So maybe self-attention has access to every single sequence, to every single token in your sequence all at once. And so it can kind of make the inference that Andreas saw someone and therefore saw maybe is important for binoculars. So it prioritizes Andreas and binocular, that connection. Cool. What if we replace that with linear, or with something recurrent, right? So there's a link between Andreas and binoculars, but as we feed every token into the sentence, by the time we reach Toby, it could be that the Toby connection to binoculars is far stronger, especially if you have some sort of decay. That Andreas is going to have decayed quite significantly, and Toby's going to take over the binoculars, right? So how do we kind of overcome that issue? How do we, you can think of it as attention as too much information, right? Obviously, our brains aren't doing matrix. Well, we're not thinking of every single word. I've said a fuckload of words so far, right? You're not thinking of every single word I said and finding some sort of correlation with every single other word I said. Our brains can't do that. And yet RNNs are more structured like our brains, but there's not enough information. How do we get around? Right? That's where we're going. So I think what paper was it? It was a paper called Metaforma where they said, look, it's not self-attention that is the reason transformers are winning. It's the constituent components of self-attention. Can we take some of those constituent components and apply them to RNNs? So what are they? Token mixing. Token mixing implies mixing information over time, right? Mixing Andreas with binoculars, mixing Toby with binoculars, etc. Right? And in self-attention, that is done via matrix multiplication. Every token has access to every single other token all at the same time. Channel mixing. Every single token, Andreas or subparts of the word, the name, the beautiful name Andreas, is represented by some d-dimensional embedding, right? It's the channel mixing, and maybe those various elements of that embedding represent different semantic features. So I don't know, maybe an LLM is like that Andreas is an esteemed scientist, or maybe he's a musician from, I don't know, California or whatever. There's many Andreases out there, and so you're capturing a lot of different semantic representations of Andreas. And so channel mixing is taking the parts of that and mixing it with other different elements of other tokens in order to try and make sense of fully recognition. So it's distinct from token mixing in that your timing, channel mixing doesn't care about time in a way. Then the other components are residual connections and some form of layer normalization, and the latter two are purely for enabling gradient flow through a ridiculously parameterized model. Okay. So, like I said, the metaformer view is that it's the holistic integration of these four components that enable such wild performance with language models. And hopefully you've identified that RNNs, recurrent neural networks, or spiking neurons, which are one specific class of RNNs, are another form of token mixing, right? Of course, by the time Andreas and Binoculars saw each other in the sentence in the model, the Andreas information had kind of faded, but it's still mixed, right? And so that is another form of token mixing. Now, we're trying to think, what are the alternatives to self-attention? Let's take these components, smush them together, these four components, smush them together. What do people do? Full-length 1D convolutions in RNN seem to be what most people have done in the past couple of years. So let's take a look at what full-length 1D convolutions are. What is this picture? This green varying matrix can be thought of as this column here could be my first embedding of Andreas, so the first word embedding. If I step to the left, that could be my second word embedding, so saw. And then that could be binoculars, Toby, whatever. So each of those are the next word token. Down here in this blue matrix is my 1D convolutional kernel, right? And these are going to be convolved with one another in order to generate some target embedding that then gets downstream processed through the rest of your model. So let's scan across. We're going to go ahead and element-wise product in this step, and then we're going to do another step in the scan, another step in the scan, and that just kind of keeps going. This is the approach that was kind of taken in Rakov-inspired GPT, and in Inspired GPT, you can recast this 1D convolution as a recurrent equation. I mean, everything's happening step by step, but of course, there's a bunch of problems that you run into. So you might think that this may be good for long-range tasks, and intuitively, this kind of makes sense because your first token and your final token interact, right? This picture here, in generating the target for embedding, everything sees everything else, right? So from this 1D convolution, if you just set your convolution length to be the same as your input sequence, then maybe you can get long-range performance there.
But so what you try convolution is just a vector multiplication.
Yeah, with the addition of sliding that kernel across in the same.
But you have to understand the data structure, which is this side.
So I'm not going to defend the nomenclature of the 1D convolution here. I think we can all accept that that's the thing that is established. Dad, stop embarrassing me. So you keep.
I don't know. I just can't understand what's picked up on this.
I mean, does anyone want to try? I've got things.
We can talk later.
Yeah, we can talk later. Codes, they only interact with the one typeset, right? I mean, as you keep going, this kernel is going to keep sliding along, and so really the only embedding that's going to feel the first and last tokens interact is target 4. None of the other embeddings are going to kind of feel each other, and so it's not going to do as well in long-range tasks. So another problem is that the hidden state, if I recast this, right now, you know what, even if I don't have to recast this as a RNN, then in either case, I'm going to have to expand the dimension size of my hidden state to just kind of include all of these various target embeddings. So if I have a much longer convolution, then you can imagine I have many more target embeddings. Those are going to be smushed away into a multi-dimensional hidden state. And so it's not as expensive as matrix-matrix multiplication, but it's also not as cheap as a linear RNN. So yeah, your inference complexity is a little higher than that of an RNN. And so yeah, it doesn't perform as well as self-attention as a result of not having all of these kind of features. But as a result of being more complex than RNNs, let's just focus on RNNs. That's where we want to go. So RNNs as an alternative to self-attention, what have people tried? What are the challenges with it? And what did we do? Challenges of backpropagation through time. I alluded to the benefits of nonlinearity in order to train your modeling parallel. It still relies on vector matrix multiplication through time. And it also has poor long-range performance in its most naive form in order to update the hidden state. So let's start off with just looking over that crop through time. Very quickly, if I go ahead and fire these animations up, this is that original spiking neuron model unrolled over time, just one neuron. Everything that goes in the forward pass needs to come back down in the backward pass. We get a series of delta, the partial derivatives of your loss at every time step with respect to all of these weights. These weights are all shared over time. It's the same weights just being reapplied to various inputs. Then I go back and I just do this iterative application of the chain rule again and again. I'm just going to kind of fly through this. So those are all my non-temporal backward pathways, but you still have to go through backwards in time.
And so there's no really lateral interaction whatsoever.
There's no lateral, that's the lateral interaction. It only goes through beta. So beta was my recurrent weight in a way. That's the only pathway to go backwards through time. And so that's your pathways that go back one step. These are your pathways that go back 2 steps. And then we still have another pathway that goes back 3 steps. So this becomes very messy just for one neuron. And you can probably appreciate that the complexity of this is going to scale as you have a longer context window, right? So the complexity of the number that scales with the number of neurons multiplied by your sequence length. If I want infinite context windows, infinite complexity. So what do we do with that?
What is in order? I mean, what is the order of complexity that still we are against just different models use? I mean,
you mean with state of the art stuff? What's GPT-4 at the moment? Is it like I'm okay? Last time I looked at it, it was it's like 1632K. Is anyone done that? Longest context?
yes,
Not the longest. Okay, sure.
yes,
The longest. 2 million.
the medium.
And what about models that, like, I don't know, Anthropic stuff and GPT stuff? Do we know?
128K is Larry's bottom. You get 8K, and then the various is on the rotary.
Okay, so for Zoomland, we expect that they get trained on 8K-ish, and then using some sort of hacks and tricks, they're able to extend them to 128K, did you say? Or longer. Cool. That's kind of crazy because what was it, just a couple of years ago, we were talking 1K, 2K, right?
Yeah.
So things have kind of exploded. So how do we get around this? So backdrop through time can effectively be addressed by removing nonlinearities over time. That's alluded to it already. It's trainable using a parallel scan algorithm, kernel-based method. Some people will also remove learnable parameters over time. I don't think that's as necessary for improving computational complexity. But it turns out from the papers that I've seen, it doesn't help too much. But we can argue about that later. Some people might also have this concern that removing your nonlinearities over time might break the universal function approximation theorem, right? And this is kind of easy to get around, right? Because it turns out that as long as your linear token mixer is preceded by a non-linear channel mixer or a dense layer, whatever it is, that's sufficient enough. That non-linearity right there is sufficient enough to be able to approximate things universal.
I mean, typically, isn't dense layer what is used?
Yeah. Dense layers are basically the most common channel mixer, or at least 3 dense layers in parallel.
Right.
So yeah. And so yeah, that's what people already kind of do with linear RNNs, right? So there are from what I've seen, I feel like there's 2 general types of linear recurrent models. Those where over time you've got some exponential moving average, so like a spiking neuron model that just decays. So we call that a static decay because the decay doesn't change in its native form. But what we also see is where you have gating mechanisms included. So your decay rate may now be a function of your input data or your input activation more general. And so that becomes data dependent. Your beta, your exponential decay, your relaxation is going to be a function of whatever your input data is. And I think Nicole brought those up when she was introducing the LLT topic area. So let's say we've addressed backprop through time. As long as you have linear recurrent connections over time, you can pass all of your data at once, your 8K tokens, and then you can kind of, within log n time complexity, you can acquire all of the gradients that you need without having to iterate step by step quite efficiently. The next challenge, we still rely on vector matrix multiplication. How can we eliminate that? So if we cast our minds back to the vanilla RNN, we've seen this equation already, just the hidden state update equation. What we're really doing here is we're performing this, like, I don't know, this D by D matrix. Actually, you know what? Let's compress this representation into this next line's form. And if I was to go ahead and calculate the next hidden state at t equals 2, it's the same equation where everything is incremented. But what I'm going to do here is substitute this line into, so V1 into here to expand this out. And what that leads to is my dense weight matrix being squared. So I've got this, I don't know, if my dense matrix is D by D, then I'm doing a D by D times a D by D operation. That's something like n cubed complexity of matrix multi, right? But I think that's now like O to the 2.38, something like that. Some fancy algorithms that have accelerated matrix multi, but that's at present the best I can possibly do. And also those numbers stop meaning very much the moment you have to offload the cache from a matrix multiply into your memory. It's like, maybe that, yeah, the theory is all well and good, but in practice it's quite a pig. On the other hand, we've got linear SNN. So with spiking neural networks, we removed that dense operation. We replaced it with a Hadamard product. And we expected that we might lose a certain amount of expressive capacity in our model in doing that. It turns out that that's not actually true. Let's see why. Same sequence of equations, just with the Hadamard product. What we can do is we can treat element-wise operators and make them work just as well using some sort of diagonalization, some sort of matrix diagonalization. So with spiking neural nets, the weight squared is just a vector, and that is going to scale that W squared. And then if you go one step forward in time, then we get W cubed. All those operations are just going to the complexity. It just follows the number of neurons n, right? So let's see how I can break this down using diagonalization and show that these two things might actually be quite comparable to one another. So almost every matrix, every square matrix can be factored into the product of an invertible matrix P, a diagonal matrix D, and the first matrix P invert. I swear this will be the only math-heavy slide, I think, hopefully. Now, when you multiply the matrix by itself, what's going to happen? So we've got our hidden state equations. We can expand W squared out, right? And we get that thing. I'm not going to read it out. Your P inverse multiplied by your P identity, get rid of that. Then we end up with D squared. And now what we're doing is squaring the diagonal matrix. And we already did that with the SNN. We just squared every element of the vector. That means we, again, get the benefit of n complexity. Yep. So that is just n operations rather than n cubed operations. Anyone identify a major problem with this?
The eigenvalues.
The eigenvalue. Okay, so the eigenvalues are something we definitely want to think about, and I have thought about them, so we'll get there. That's great. Great point. Anything complex about this?
Well, it's not what I'd say.
The decomposition.
The decomposition in of itself isn't expensive, but this calculation of this inverse is expensive. Yeah. It's a pretty damn big matrix, so that's going to be quite expensive. What do people do about that? They say, fuck it, let's not take the inverse. They just replace it with another level matrix. Sure, if you so desire. There are cases where you can't get away with that. I think I'll give you a bit of intuition on when you get. As that's a cool point, though. Cool point. Terrible adjective. So, what are we going to do with this? People generally just replace that P inverse, and what that means is that you're no longer represented by this exact recurrent weight matrix. But who cares? Deep learning is a very empirical science, and it works. It turns out by adding additional learnable parameters, still get good performance. I think that trick comes from Mumbo.
And so you let each other be Q.
You're learning Q, you're learning P. Yeah. Yep. Great. So while we no longer have a perfect correspondence to the original weight matrix, we now have an additional learnable layer, and it ends up having better capacity. And of course, D only changes with increasing sequence length. So really that's just D to the power of whatever sequence step that you're presently at. So it's just an element-wise operator in your recurrent pathway. It's still linear, right? No sequoid, no nonlinearity. And I think this is like, it's quite cool because if I was to take my, we've seen this picture before, right? I said that a lot of people are taking the nonlinearity and throwing it into the dense components of their networks, and then their linearities are just in the recurrent parts of their networks. This maps perfectly to that, right? Your nonlinear channel mixer is just key. Your linear token mixer, that is mixing information over time, is just your D at the phrase to, I say N here, really, it should be whatever time step you're at. And that gets fed into another nonlinear channel mixer. So everything I said about the universal function approximation theorem still being kind of holding true is held up here. That's quite nice.
Is it at the end of the day? So this.
Yep.
Why is P in London? Yeah, like these are actions. These are like normally.
Oh, sorry. You can add nonlinearities between them. You can arbitrarily.
Yeah.
You're already not going to be your W matrix. So why not just keep going and add nonlinearity? I wish I could give you a more satisfying answer, but that is deep play.
So if we look at computations, it's full dense that shouldn't be, would be where the action.
There's a lot of Q and Ps. There's a lot of Q and Ps going on already. Okay. You've already got a lot of linear layers, so what's another two in your recurrent module? What I do have to say about the spiking neural net link is that it's nice because we've already been largely doing a lot of this already. Right? If I bring up that SNN kind of picture, then you've got a linear layer with some nonlinearity that gets passed into a recurrent form, then heavy sided, and so it's basically nonlinear linear recurrence, ignoring reset, followed by another nonlinear dense layer. So I don't know, a lot of these principles have already kind of been adopted by the neuromorphic community without realizing, I guess, the theoretical significance of them.
What do you get to work?
Cornelia, you want to mute your mic? That'd be awesome. So another observation, to go back to your eigenvalues point, if you have real valued the eigenvalues in that B matrix, then you're just going to get static decay. If you instead allow for complex eigenvalues, then your hidden state is going to oscillate. You're able to, if you could just do the recurrent equation again and again, your hidden state will go up and down. Cool. That oscillation is somewhat significant because if you think back to positional embeddings and self-attention, the GMT20240705 paper used some sort of sinusoidal embeddings, sort of oscillations. I think now state-of-the-art models use some rotary positional encodings, which also has some rotary in its name, therefore something oscillatory. So you can still acquire some level of that representation through complex eigenvalues. We don't use complex eigenvalues because in our experiments, real valued eigenvalues work better. I don't know what to tell you. So we've basically gotten rid of vector matrix multiplication. The only thing that really had to happen in the recurrent pathway, so this is just the recurrent pathway, was d squared, d cubed, d etc.
So just how do you get up the corporate side? You make it symmetric?
That's just something that you can initialize basically. How do you get rid of it? So a lot of people represent it. Yeah, you deep learning that shit, right? Just do whatever the fuck you. A lot of people will represent that D matrix using but just using a pair of D values. One is your 90-degree complex axis, and one is in your real axis. And drop one. It's really, it is more complex than it sounds. Probably that.
If I purely get the government, if the current not with here, on all this, right?
Yeah.
It's fine. That's like compute the values.
Yes.
Instead of really doing recurrence, so you're unrolling it, saying that if I have 3 steps in my recurrent network, then it's like having W of W.
Yep. So the purpose of all this linearity and reduction of computational complexity is to just unroll everything and be able to compute everything in parallel, all of your states in parallel. Why is that? All right, well, let's say I have a model with a nonlinearity over time, then, okay, maybe that model in theory can represent more stuff than my linear model. Problem with that is in the time, given 2 weeks of 8 in my GPU rack, then I will be able to train on like 100 billion tokens in my linear model versus 1 billion tokens of my nonlinear model, right? And as a result of that, my linear model is going to outperform given the same training time. That's given the same training time, because that's really what we're about. Core long-range performance, one of the most critical things here that we have not yet addressed. 5 minutes left. This is going to go over time. Core long-range performance. So what do people generally do to address long-range performance? Gating mechanisms. This goes all the way back to LSTMs. They have control gates, they have forget gates. Quick refresher, control gates do this thing where, as your hidden state value is moving forward through time, your control gate says, all right, is that hidden state ready to be passed on to the next layer? Or should I just hold on to it for a little bit? Should I control it, just keep pushing it along? So it's kind of like a enabler, right? The forget gate says, all right, this bit of information is not useful to me. Let's get rid of it and make space for something more important. But that's something that a lot of people do here, because historically, recurrent neural nets have really fallen short in long-range performance. So gating mechanisms, that's all good. They both improve gradient flow. They optimize how model capacity is used. Second, regularization. I think Nicole, again, mentioned how you often want to initialize your recurrent weights to be close-ish to 1, so you don't fall into the trap of vanishing or exploding gradients too badly. And thirdly, temporal residual connections where you project information forward in time. In matmul-free, we just use the first. But there's a lot of works that have incorporated gating mechanisms into linear recurrence. This has helped, but we can do better. So let's dig into it a little bit. But it turns out that forget gates haven't really been exploited by the linear RNN literature too much. I think we started to see good forget gates and come into the hierarchically gated recurrent network architecture, the HGRN. If you want to look into it, let's give some intuition. Let's say we just have one neuron unrolled over time. So if I have this one neuron trying to represent multiple units of information, let's say that this blue ball is 1 bit, that gets passed into my model. And then let's say the next step, I have this yellow ball that gets kind of blended and mixed with this blue ball. It's hard to disentangle the two of them, and that continues being projected forward in time. That kind of sucks. You're mixing everything together. You don't know what bit of information is important for, I guess, what other task or other token. On the other hand, if all I care about was my yellow bit of information, then maybe I need to forget that blue dot first. In order to forget that blue dot, then I need a forget gate. It is the most important part of an LSTM. Hasn't really taken off in the state space literature. If that forget gate is set to 0, then you scale the hidden state by 0 and you forget previously stored values. On the other hand, if it's 1, you keep projecting the same bit of information forward through the hidden state. So let's see what this looks like. In this picture, my blue bit is going to go forward. It's going to be scaled by 0, it disappears. Then the yellow bit has all the latitude in the world to just keep getting projected forward in time. And at the end, all I have is the information I care about. Hopefully your model is able to learn that in an effective way. Forget gates are extremely susceptible to vanishing gradient problems. They're only really, so this might be falsifiable, but they're really just useful to us as 0 or as 1. You're getting something or you're remembering something, right? And typically with forget gates, you're often passing them through some sigmoidal non-linearity. And so if you're on either end of that sigmoid, a lot of vanishing gradients happen. So if you're stuck at 0, you're going to be at 0 forever. If you're stuck at 1, you're at 1 forever. And so you're sitting at these values, and it's hard to perturb your way out of those values, right? Now, if we looked at the brain, broke it up into various layers, etc., because that is what the brain is, then you might be able to successfully guess that the time constants in lower brain, in the lower parts, in the lower layers are going to be short, that they're just focused on local information, local connections, local sequences. As you go higher and more depth into the brain, you're trying to now get more context. You're trying to contextualize different embeddings of information and make sense of the world around you. What do you do with that? You're going to end up having time constants that are considerably longer in higher brain regions. So with that being said, what we did here was take these forget gates and basically set a lower bound on them as you go, and that lower bound is going to increase as you go deeper into the blocks of your model, right? So in order to kind of force that, we just kind of randomly initialize this. There's a bit more detail to this, but we randomly initialize this the parameters associated with the forget gate. And we just accumulated, we did this like cumulative sum operation in order to force the higher layers to have larger forget gate values than lower layers. As a result of that, that lower bound just being an additive term to the forget gate basically helped with all vanishing exploding gradient problems with the forget gate. In comparison with attention, there is no forget mechanism, but you're stuck with excessive information. Too much information then, so you could argue that recurrent neural nets have kind of like the correct amount of information when you introduce these kind of factors. All of those were snowballed into this, like, into the matmul-free language model. High-level overview, let's just move forward. It's the first billion parameter scale matmul-free model to achieve language generation. Like another 10 minutes, we call with that. I'm going to keep going. All of your dense operations are going to be all of your dense parameters, all of the weights in your dense layers are basically replaced with ternary parameters. Microsoft did it with BitNet. They didn't open source their model, so we just took them for their word. If you do that, your multiply is replaced with a sign accumulate. In order to train those models, you just use vanilla quantization aware training with straight through estimators, etc. Our attention map is replaced with everything I just described, with your linear recurrence, with all these forget gate mechanisms. And then finally, we went ahead and did this custom FPGA implementation to actually make it useful. Obviously, GPUs are not optimized for ternary weights. So what you feel something that was. The first two are what enabled this model to be matmul-free. Last one is what makes it useful. If I kind of break this down a little bit, self-attention can be, it just involves taking this input embedding, passing that through these 3 parallel layers, splitting off into these. There's a bunch of operations there, which I don't need to go into. But then ultimately, you're left with this kind of pink vector and this dark gray vector that are projected forward into time. You can see my cursor, yeah. And you can see that these are concatenated to your next hidden state. And so as you go forward in time with self-attention, you're just extending out your KB cache, right? As a result, you're going to have a significant amount of memory bandwidth issues from that. So that's depicted in the bottom row. The KB cache increases with growing context length, and that's a result of having to do matrix-matrix multiplication. Your matmul-free operator is quite different. You just have your hidden layer pass forward in time. And if I kind of highlight this area, you've got the sigmoid as your forget gate vector, and you're just left with a bunch of Hadamard products. So we have ternary dense layers, right? The outputs of those are not ternary. They're going to be, well, with training, we use BrainFlow 16. Everything from there was just processed using Hadamard operators that took all of the forget gate, its concepts and principles and element-wise linear recurrence into consideration. And you end up with a hidden state that just replaces the previous hidden state rather than chaining it further and further along. So that's all well and good. If I break this down, the challenge of backprop through time is removed because you have a linearly recurrent projection of your hidden state. That's reasonably easy. Reliance on vector matrix multiplication. So all of the tricks with element-wise linear ops, that's gone out. And what's highlighted here is just the replacement of your linear parameters with ternary weights. That's removed as well. And for long-range performance, everything I said about forget gates come into play in the hidden state operators here. So get rid of that issue as well. Can't we just ternarize pre-existing LLMs to get rid of matmul operators? No. We went ahead and used Transformer++ as the baseline for comparison. It's the backbone of a lot of state-of-the-art models, variants of it at least. So Llama 2, Llama 3, Mistral, and a few others. And much of the recent literature on linear recurrent models use Transformer++, and that was not able to converge, just using state compute resources. Optimizations to GPUs, I'll fly over this, but this is obviously something that is really milked when you're not processing on GPU for inference only. It's matmul-free and inference only, so we're not getting matmul-free in training, right? We're still doing quantization of our training. But we went ahead and did some optimizations to GPUs in order to actually speed up training. We had to meet the nearest deadline, but going to fly over this. So we built some custom CUDA kernels that just did fused operators with with layer normalization along with bit linear layers that use ternary parameters. So that helps get a speed up of 25% for training and a more effective use of your VRAM. And we also did wrote a custom CUDA kernel to do inference better. Cool. 10x less VRAM during inference there. Now, I think that this is something kind of important. So this graphic is taken from a preprint from scaling laws. As much of a law as Moore's law is a law. So neural language model, this plot in the middle shows the test loss almost linearly decreases with increasing data set size. You're given a curve fit as well. The plot on the right is how your loss decreases with increasing parameter size. And this on the left, your compute is just kind of like a product of those two things. So yeah, it's the plot on the left is the product of these two things, where PF days refers to petaflop days. Then it's more about how your test loss is going to drop with the increasing compute. So what they no, it's from OpenAI. Yep. What they note is that for optimal performance, all three factors have to be scaled in tandem, right? So inspired by that, we went ahead and explored the scaling law of our own model. So you'll see on the y-axis, this might be a little bit difficult, small text, but you've got test losses in clusters of 2. So one of them is Transformer++, not turnerized or anything, just vanilla Transformer++. The other one is the matmul-free. They kind of follow the same trajectory. Transformer++ at the bottom is marginally better, but if you keep projecting these things, then you notice that the test loss gap decreases as your model scale increases. So that gives us a bit of hope that there might be a point where, let's say 10 to the 22 or 10 to the 23 training iterations will be able to kind of match that performance. I should note that this loss thing is a little bit inaccurate because we're using ternary operations. They're using full precision. And so if you were to normalize to that, we should all open. Cool. So a bunch of other things. I'm going to leave that for you. We tested on a few different benchmarks. I can fly over this. Point is, as your parameter scale increases in size, the gap between Transformer++ and matmul decreases. The only outliers were the data sets that had multiple choice or some sort of classification 1-0 answer. So a bit of randomness kind of is introduced there. I should mention that we're only comparing against our own in-house trained Transformer++ because it's really hard to do these things fairly. So our model was trained on 100 billion tokens. So you'll see models that do way better at 2.7 billion parameters because they've been trained on 15 trillion tokens. So that's not really a fair comparison. This is the compute that we had, that I guess had available to us. We went ahead and did an FPGA implementation. So the final technical stuff that I really want to talk about is testing across a few different embedding dimensions. We managed to achieve 23.8 tokens per second at 13 watts. This is a very unoptimized implementation as well. This high sliding. We're not even doing DDR bursting. We're not using DSPs. This is just raw system Verilog. And that's good. If you compare it to the brain, you can probably read tokens at 5 to 15 per second at roughly 20 watts, probably. How can I make this intuitive? All right, so latency, this here just shows you that memory access was not the bottleneck, and that's probably a result of doing things like pipelining and optimization. So that might be a little bit more balanced. What ultimately took most of the time was the ternary accumulation in those linear layers. Some takeaways. Gonna finish up here. Lessons for spiking neural nets. We started with spiking neural nets and saw how there were a lot of principles we were accidentally using in that literature there. And we were able to port it over to, yes, matmul-free. They were already doing element-wise recurrence. They're only really going to be competitive in the deep learning context if they're linear over time, right? What does that mean for the reset mechanism? Maybe we got to get rid of that and come up with alternative ways to induce refractoriness in a linear fashion. Gating mechanisms are also needed. Single-dimensional hidden state is just not going to cut it. If you want to be competitive, you need to introduce big gates, control gates, and that's honestly okay. Neurons are far more complex than a single-dimensional recurrent model. Lessons for linear RNNs, going back. So forget gates are critical to account for the lack of these huge attention matrices. There's still a lot to learn from the brain. Those constrained forget gates, but I don't know, in my opinion, kind of neuromorphic. So maybe there's a little bit more there. And finally, static sparsity seems easier to deal with than dynamic sparsity. Spike GPT, very dynamically sparse, absolutely sucked when we took it to 1 billion parameters. Matmul-free, statically sparse-ish ternary parameters. So we've got a bunch of zeros, about 30-ish% of the weights with zero. That performed really well. So static sparsity seems to be something that we can tolerate well. It could be a matter of going to ternary activations for spike-based logs. Finally, my lab, they do everything, and I just talk about it, especially Rija. He's an absolute fucking star. I am mind blown at how he's done all of this in the first year of his PhD. He's just a gem. Bunch of references that you might be interested in, both the work that we've done here and work that is related. With that being said, yeah, cool. Let's move on.
So, guys, thanks for coming. I know it's Friday, it's late. We are going to do reports from our group in Maryland on event vision. And the first one is about, okay, I want to really, you have learned now about there's lots of work of flow estimation, which is really or some form of image motion representation, which we need from the event. It's the very prerequisite. And you also heard a little bit what the current approaches are, that either you fit the local planes really, which really doesn't work very robustly. Like that. And the other thing is, we try to align it. So locally, we try to estimate the parameters, compensate for these parameters, and if we compensate well, then they should align. And the way to solve this is then not in 3D, but in 2D, so some optimization, because that's the only thing that computation is feasible. And there were about 20 functions studying how you can measure and that. But now we really have this 3D method, and the idea is basically that we map the point cloud to hyperdimensional vectors. And you have got basically talked to the people in Waterloo. This encoding as wide-open compositions, but there have been many additional things done that we do not like any other algorithm when working 3D. You first need to build a tree structure, this 3D trees, in order to access it. So Dehao found a way around that. We did first work on regular XY point clouds and now extended it to event clouds. And one of the things is because the algorithm can be implemented also, it's a constant update. New events come in, and that's why it should really be implemented in robots. So we want to put the idea forth so that we can start discussing it.
I believe it's hardware friendly at some point, right?
Yeah, I mean, we have to talk about how to see it, but we will see there are ways. Okay, thanks, Dehao, and you are on.
Thanks. Thanks. Is he going to show himself so we can see him? Also, it's better if the speaker shows themselves. Can you see me?
Yeah, I like this.
Yeah, I'll tell you. I don't know how you're supposed to.
This is Dehao.
Can you see my face?
Yeah. Good to see you. Great.
Thanks. Thanks. Oh, and I can see you. Okay, great. Thanks so much for your great attention. And it's my pleasure to present my work here. Yeah, thanks Cornelia for the great introduction. So you can see the topic of this presentation is a linear time and space local geometry encoder. So I would introduce what is a local geometry encoder and why a linear time and space is significant in this project. So yeah, so it is a paper that is accepted by the by the ICML 2024, and it has been open sourced. So if you are interested in that, you could definitely check the code and check the paper. So a brief background. So what is local geometry encoding? So let's say we have the input of a point cloud, which is a n×3 matrix. So like on the right-hand side, all the points here are the point cloud. And the local geometry encoding is for each of the points in this point cloud, xj, you will get the centerized neighborhood. So in this figure, so let's say this the red star is xj, and then you want to draw a ball with radius equals to r, and then you collect all the points within this ball, and then you will get a collection of xk, right? And then you would centerize the xk by subtracting xk by the xj. So subtracting the neighboring point with the center point, and this will give you the centerized neighborhood. And then what we want to do is we want to output a geometry encoding, which is with shape n by d. So for each point, it would get a d-dimensional vector. So here, gj. So gj is the geometry encoding of the point j. So basically, you input this centerized collection of points into an encoder, and it will return you a vector. So basically, you would input the whole orange points into an encoder, and it would return you a fixed length vector. So we want this encoder E to receive a local point cloud and then produce a vector that describes the local geometry. So here we have an implicit assumption, which is the translation invariant. It means that if the whole point cloud is translated, then it would the output G would be the same. This is easy to observe because if you translate the entire point cloud, the centerized neighborhood doesn't change. So it would make the local geometry encoding be translation invariant. So that's the problem definition. So the ultimate goal is we receive an input point cloud n by 3, and then we output the local geometry encoding n by d. So that's the problem definition.
What's D? What is D?
D is like a 256 is a hyperparameter. So yeah, for example, if the local geometry is very complex, then you may expect the D to be high. But if it's very simple, like it's just a plane, then maybe D can be small. So that's the hyperparameter. And so what is the so after local geometry encoding, what can we do? So there are many different things we can do. So let's say you have input point cloud and you get the local geometry encoding. There are 3 different types of tasks you can do. First is local regression. So basically, after you get this local geometry encoding, you pass it to a point-wise multi-layer perceptron or fully connected network, and then you get the output, which is n by 3, for example. Then you get a normal estimation. You get this is what I call a local regression. So for example, a local, the normal estimation is a very typical task of local regression. And the second task you can do is non-local regression. A very typical example would be segmentation. So after you get this local geometry encoding, maybe you use a transformer to achieve some message passing, and then you get a prediction of the, like, for example, which class it belongs. So in this non-local regression, so a segmentation would be a typical example, because to identify which class it belongs, you may need to have some global information. So that's non-local regression. A typical example would be segmentation. And the third one is condensation. So a typical example would be classification. So for example, if you receive the point cloud and then you want to classify that this is a plane, then you can do is you get a local geometry encoding, you use a fully connected network, and then you do a maximum pooling on the first dimension, and it will give you a d-dimensional vector. So this is condensation. So basically, a local geometry encoding is a very fundamental task. That's why in this paper, we want to tackle this fundamental task efficiently and robustly. And before going to our method, I want to show you how existing methods deal with this problem and what are their problems. So they usually follow a grouping and downsampling pipeline. So let's say you have the input point cloud, which is n by 3. First of all, in order to compute the local neighborhood, you need to compute a mutual distance matrix. So this can be very memory intense because it is an n² operation. So imagine if your n is like 10,000, this is already medium scale, not a large scale. So even if it is 10K, this is already terribly large. So this is the first bottleneck, compute a mutual distance matrix. So after you compute this mutual distance matrix, then for each point, you would extract the neighboring point and then sample K points from this neighborhood. and then do the centerize, and then you will get an n by k by 3 matrix. And typically, it would involve a multi-layer perceptron to map the n by k by 3 into n by k by d, and then do a maximum suppression in the d dimension, and then it would become n by d. So as you can see, this n by k by d is also not very good, because let's say if you have a 10K point and then you want to consider 128 neighborhood, so let's say k equals to 128, and then your d may be like 128, then this is also ridiculously large. So it would also be a bottleneck for both computation and memory consumption. So basically, the existing method, regardless what they are using, they would encounter two bottlenecks. The first is the memory bottleneck, which is the mutual distance matrix. And the second bottleneck would be this n by k by d. So how do they deal with that? They usually downsample. For example, here, instead of computing n by n mutual distance matrix, they just downsample the entire point cloud, for example, by 4 times. Then you only need to compute the n divided by 4 by n mutual distance matrix. So they need to do downsample. And similarly here, if you have a very large neighborhood, then usually they would make this k very small. For example, k equals to 16, then it can reduce the bottleneck. However, you can imagine this will induce many information loss, especially when your local geometry is complex. Then if you use a small k, then your local geometry encoding will not be like descriptive. So that's the problem. And so what our paper trying to solve is we propose a local geometry encoding that is very efficient to compute. So here I draw the diagram, the computational diagram here. As you can see in this diagram, there is no any bottleneck. So there are n by p, n by d. So I will introduce later what is p, what is d. But usually p is like 4,000, and then d is only like 256. So if you see the dimension here, there's no bottleneck. There's no such a like n by k by d or n by n. So they are very efficient to compute. And of course, I will introduce later why it can be computed in this way. And on the other hand, it is also very descriptive. So, a local geometry encoding, you want to describe the local geometry, and therefore it must capture the geometric feature. So if we see the clustering of the raw vectam encoding, so our method, I named it vectam. So it is vectorized kernel mixture. So I will introduce why it is named like this. So basically, if we do the cluster of the raw vectam encoding, you can see it already gives you a very nice clustering of the geometries. For example, this plan, this is a very this is a plan, and they are clustered together. And this is the leg of the chair. It is clustered together. So as you can see, our encoding is very descriptive. So and third, it is very robust to noise. So if you add noise to the point cloud, and then you compute the local geometry encoding, it is pretty consistent. So you can see the lowest similarity is 0.75, and in majority time, it is higher than 0.9. So it is robust to noise. And finally, it is very simple to implement. So to implement the vectam encoding, you basically only need this 6 or 7 lines. So you initialize a matrix A and B, and then do a matrix multiplication, and then do an exponential I. So in case you don't know, this is a cosine plus I sine. So this is the Euler formula. So basically you compute this matrix, and then you put it here, and then put it here. So this is a very quick operation. So you get this x multiplied with A, x multiplied with B, and then you get you do this operation. And finally, the local geometry encoding is just by this simple matrix multiplication. So I will introduce later why it would be so simple. So Yeah, so if you only have one thing to take away, and for example, you don't want to know what's the theory behind, then this will be the most important thing in this presentation is the implementation of backend encoding. And when you have this, you can already implement it and then use it in your own project. But later on, I will introduce the theory behind. So why the encoding is called backend? Because it is vectorizing a kernel mixture. So a very key observation here is, let's say if you have xk, which is the collection of points, then if you compute G using this formula, it would encode the density distribution of the collection of points. So if you look at this figure, here on the left-hand side is a shape distribution function. That's, you can imagine this is the underlying shape. And then from this underlying shape, you can sample the point cloud, which you get a collection of points. And then by this formula, so you compute this G equals to this, and then there's a formula that can help us reconstruct the distribution from the encoding G. And as you can see, this reconstruction is very similar to the original distribution. Why is the case? It is because this encoding is essentially vectorizing a Gaussian kernel mixture, where this Gaussian kernel mixture can approximate the original distribution. So it will close the loop. So from this distribution function, you sample the point cloud. From this point cloud, you compute the backend encoding. And this backend encoding approximates a Gaussian kernel mixture. And this Gaussian kernel mixture can approximate the original shape distribution function. So that's the reason why backend encoding can encode the point cloud. It is because it is encoding the density distribution of the point cloud.
Ask a question. What is
Okay.
it? Where do you get A? Where do you get A, and why do you use complex? Is it exponential of a complex matrix?
Yes, that's a great question. So here, A is a 3 by D matrix which follow normal distribution 0 sigma square. So here sigma square is a hyperparameter that you can choose. So this is basically a kernel trick. So the reason why I use this exponential, it is because a Gaussian kernel which is exponential sigma squared and then x minus y distance. So this is a Gaussian kernel. This is a Gaussian kernel. And then it can be approximated by exponential I x a and exponential I y a. So because of this approximation, that's why I use this exponential I. It is actually inspired from a paper called Vector Function Architecture from Paxson Freddy and from Berkeley. So I think you can the details are not you can check the details offline, but the major intuition here is the Gaussian kernel can be approximated by the inner product between the two vectors. And that's the motivation why we use this exponential I matching. Does that answer your question?
That's sort of.
Okay. Yeah, so if you...
It's good for now.
Yeah, so yeah, if you have any question, you can we can talk offline. So I want to go too much details here because we'll only have a few minutes. So yeah, so to formalize that exactly, then it is a theorem that formulates the previous intuition. So let's say you have the neighborhood of point x0 to be this, and then the local geometry encoding would be equals to this formula. It is just a summation of this exponential I and then xk minus x0. So you just input this point here, and then here A is a fixed random matrix where they draw from normal distribution. So this is a kernel trick. This is a kernel trick. You can see the paper in details. Yeah, and that's it. And then so previously this is about point-wise local geometry encoding. So the input is a single point x0. So if you compute dense local geometry encoding, it means that for all the points you want to compute the local geometry encoding, then you can say here we can like write it into a matrix multiplication. So you can look at this formula. So this formula it is just a matrix version of this. So here J is the adjacency matrix. Adjacency matrix where J equals to 1 if they are neighborhood and 0 if they are not neighborhood. So so basically if you write it into matrix, then it would be this. Okay, so now you can see the formula is already very simple. You compute this x multiplied with a and then do an exponential mapping, exponential I mapping, and then you multiply this A matrix with the adjacency matrix and divide it by the A matrix. Why we can do that? It is because there is a very nice factorizability here. So if you consider this is equals to exponential I xka divided by exponential I x0a. So so basically that's why we can factorize the xk minus xj into this division, and that's why this is the element-wise division here. So basically the ultimate version, not ultimate, this intermediate version of vector encoding is this. First you compute the adjacency matrix, and then you compute this A matrix, which is x multiplied with A, and then use an exponential I mapping. And then you multiply adjacency matrix with A and then divide it by A. So that's the version 1, dense local geometry encoding. Okay, so continue. So if we do that, then we will still need to compute this very expensive adjacency matrix, right? Because it's still n squared. However, we have an important trick here. We would replace this adjacency matrix with exponential decay. So you can see the adjacency matrix, it is like this. So when you reach the radius r, you would decay to 0 immediately. However, we can replace it with exponential decay. So it will look like that. So this is this formula. And after we replace the adjacency matrix with this exponential decay, then we can approximate this adjacency matrix with a matrix multiplication. So yeah, basically, if you look here, this J will be replaced by this B by B Hermitian. So Hermitian is kind of transpose. And after we do that, you can see we can do this matrix multiplication first, and it give you a P by D matrix. And then we do this, it will give you M by D matrix. Then this will it eliminates the need of computing this M by N very expensive adjacency matrix. So that's the major idea behind. So now we achieve linear time and space. So that's the ultimate version. Yeah, I explained all the the theory behind, and this is the ultimate version of the backend encoding. Okay, so after getting that, we can see what's the runtime and memory cost. So if you can imagine that when your number of point cloud, your input point cloud size increase, the gap between existing method. So here, all the three are the existing method, and the black is our backend encoding. So the runtime you can see is already 100 times faster than the existing method. And especially when your number of neighborhoods increase, then our advantage will be even larger. And especially when the problem size increase, this already runs out of memory for those existing methods. But for ours, we are running this experiment on an 8 gigabytes GPU, and it can still scale to 100K and a very large neighborhood size. So it demonstrates the very strong scalability of our method. And here are some experiments. So it's a normal estimation task. As you can see, our method not only is the most efficient one, but also the most robust and accurate one. So this is the degree error. So yeah, this just some experiment. And here we can also have a illustration. So we can so this is the local point cloud. We can plot. So a very nice thing is we can visualize how good is our encoding. So as you can see here, it almost reconstructs the distribution of the point cloud. And even if there is a noise here, so I think from the point cloud, it's already hard to see the shape, but our webcam encoding can capture the shape. And also when there are density variation, you can still kind of capture the shape of the local geometry. So this is another nice thing where our method can visualize how good the geometry encoding. And there's other tasks like classification. We can achieve better accuracy with much shorter running time, and also some segmentation experiment. We are better and then faster. And finally, a semantic segmentation. We are better and faster. So yeah, those are some like experiments we need to run to evaluate the method. So I won't go into too much details here. And so I want to introduce the extension of this webcam encoding. As you can see, this is a very fundamental algorithm that can be applied to many different tasks. So here, one task will be a real-time optical flow or normal flow estimation from event camera. So here, so recall, after local geometry encoding, we can have different tasks. So in this problem, we will focus on this local regression. So the input is a point cloud. In this case, it's an event camera, event streams. So event stream is XYT. So it is also three-dimensional. So it can also be regarded as a point cloud. It is very simple. So in this methodology, we just slice the event. So basically, if you have a stream of event, and then we will collect the event within a time interval. Let's say this is 20 milliseconds, and then maybe you collect 50,000 events. You would just input these 50,000 events to backend, and then it will give you a 50K by maybe, for example, 256. And then you pass to a multi-layer perception. It gives you 50K by 2, which is the predicted optical flow. And then we just train it end-to-end supervisedly, very simple pipeline. And then it turns out to be very good. So we can, first of all, we can predict the per event optical flow or normal flow within 20 milliseconds in 20 milliseconds. So it means if you want to predict the flow within 20 milliseconds, it only costs you 20 milliseconds. So it is real time, and it only has 40 milliseconds latency. Because you need to collect events for 20 milliseconds and then spend 20 milliseconds to compute the flow. So it only has 40 milliseconds latency. And it turns out that the result is very good. So I will show you a video. So this video is on the bottom, it is the ground truth optical flow, and on the top, it is the predicted optical flow. So yeah, and this is the norm, this is the angle, this is the flow, and we also have a confidence measurement. So basically, we only predict flow when there is a high confidence. So yeah, so as you can see, this is quite reliable and quite sharp. And even if there's a large motion or small motion, it can still gives you very good prediction.
Looks beautiful, but I still don't understand. What's the principle of the optical flow computation here? Can you go back to that? And
Okay.
do you have to, for each frame of data, because you have frames here, for each volume of data, do you have to compute this gigantic MLP with 50,000 times 256 input? That's a huge MLP, right? Isn't it?
Yeah. So if you have 50K and then by 256, then for example, if your MLP layer is 256 by 1, yeah, you basically you need to compute this very giant MLP, but this is actually quick in GPU architecture. This only costs you a few milliseconds. So this is actually very quick.
50,000 times you have to compute that 2-layer MLP. Is that correct?
Yes, yes.
No, really, just
Actually, that's why we're here, because it could also be implemented.
no, but I just don't understand the method. What is the principle by which the optical flow is computed here? Can you go back to the principle? By what principle is it estimating normal flow? In the previous slide, maybe you showed it. What's the principle of the optical flow?
Okay. So in this slide, so input is the event. So this is XYT.
Yeah.
So, yeah, and then it would, so here M would be, for example, 50K, because if you collect the event within 20 milliseconds, is about 50K. So after you get this 50K by 3 matrix, you input to this local geometry. So this is our backend encoding. You will get a 50K by 256. So it's a 50K by 256 matrix. And then you will input to a point-wise multi-layer perceptron. So it would be a sequence of 256 by 128 and then 128 by 2. This is a multi-layer.
Which has been trained on labeled data to estimate normal flow?
Yes, yes. We use
That's part that's missing. Okay. Trained on labeled data to estimate normal flow.
Yes,
But
yes.
automatically, you know, our data sets will automatically.
Okay, that's the piece I was missing.
Yeah,
Okay.
various data sets that we collected, the
So
CTR already be able to.
Yeah, so,
So there's-
so for each event, you're not to basically do how many max? How many max do you have to do for each event? How many multiply accumulates?
Sorry, how many what?
How many max per event is required? 256 times 128 or something more.
Yeah, so for each event, it is 256 by 128 plus 128 multiplied by 2, because it is a 2-layer. This is per event. And then you would need to 50K this, right? Because you have 50K event, and for each event, you would compute the multi-layer perception from 256 to 128, and then from 128 to 2. So it is 256 multiplied by 128, and then plus 128 by 2.
But that means for each event, you have 128 output in the first NLP, right? So each event has 128 weights in the first layer. That's what you're asking, right?
Yeah, maybe I'll do it on the blackboard later. Just to understand the actual numbers. I can't tell for this. Yeah, so far.
The MLP is going from 256 input neurons to 128 neurons to 2 output neurons. And for each event, which is 50K events, right? For each event, you need to evaluate this network once. So for each event, in the input, you need to get this encoding into 256.
You have to first compute these 50K local geometric features, right? Using the previous thing.
Yes, yes.
Have to do all that math. Yeah, it's still a lot of compute, right? You have to do
Right, it's still a lot of compute, and but thanks to GPU, it is like actually fast. So
that's 100 watts. That's 200 watt GPU, right? I mean, I don't know what GPU is this, but it's still a lot of power. I mean, I'm just actually skeptical, right? You have an 8 gigabyte, that's a lot of memory. 8 gigabyte GPU running, say, 100 watts, 200 watts to run this at basically 60 hertz. Maybe I'm missing something. Yeah. I don't know what the numbers are really. I have a hard time. Yeah.
It's 700 watts.
How many max can you do extra for it?
No, I mean, I can get a sense of the amount of actual max. That's what I mean.
What's the lower bound? Like, what's the optimal way to, like?
Well, there are other optical flow methods that are much more efficient, right?
Like what?
Lucas Canaan.
So how many max would that be? What are you comparing against?
I don't know what this number is, so I can't compare it.
Maybe. Yeah, so to compute, I mean, this number doesn't it is hard to infer how quick it is from this number, of course, but from the experiment, so I do some profiling. So if you compute 50K, so if you have 50K by 3 in the input, and then after this encoding, it becomes 50K by 256. So this step will take roughly about like 18 milliseconds. And then from here to here, so you get 256 to 128 and then 128 to 2. So this 2-layer multiplier, this only takes you about like 2 milliseconds. It's actually very fast. So
On what though? What's one word?
but it is on 85,000 GPU. So it is I would say it's a nice one. So
But you can do other things with the code.
Yeah, that's right. Yeah,
You
that's
can
correct.
do now these kinds of this for segmentation. And okay, and you had also ideas you wanted to present that this could be updated, right? Then it would be interesting when you are with that.
Yeah. I will talk about some like potential neuromorphic implementation, but yeah. So no need to worry about the efficiency, but it is efficient. So from the empirical experiment, so we can make it like into 20 milliseconds easily. So so maybe we can talk offline if you are like unsure. So then so current challenge on implementation on GPU is we have to accumulate events and then estimate the flow in batch. This is not because our algorithm does not support iteratively update, but it is due to the in-place summation must be broken. So this is the backend encoding, and if you want to write it into an iterative prediction, so basically you get the event sequentially. So when you have this 1 by 3, you get this event 1 by 1, and you need to like keep track of this this B Hermitian A matrix. You need to iteratively update this B Hermitian A matrix, but this is very bad in terms of GPU, because in GPU, in order to do this, this must be blocking, so it cannot be like done in parallel. So basically, if you have this B Hermitian A matrix, then one event comes in, they need to they need to process this plus equal operation sequentially. It is not possible to have all the events do this operation simultaneously, and that's why it will become extremely slow if you implement it sequentially or iteratively. But on the neuromorphic hardware, things may be different because the in-place summation is no longer blocking. So for example, if you want to sum up I1, so this is current, this I means the current. If you want to sum up I1, I2, and I3, then you just only need to like design a circuit like this, and then you automatically get the summation, this I equals to I1 plus I2 plus I3. There's no blocking required here. So this is I mean, I'm not quite in the field of neuromorphic computing, but this is my intuition, because the in-place summation in neuromorphic hardware may not be blocking. So this will make this this step very efficient if we can implement it in neuromorphic hardware. And of course, it also saves a lot of energy. So that's the end of my presentation. So if you have any idea like how to implement that, or you have any idea, then you can talk to me or talk to Cornelia offline. So is there any question, or am I running out of time?
This is our new work, just got published last month on Science Robotics, called Microsaccade-inspired event camera for robotics. I will skip the introduction on cameras so that anyone can rewrite the this option. Skip. Yeah, so yeah, event cameras can be used in many applications. Yeah. But there's a disadvantage of event camera. It loses texture that is parallel to its moving direction. See, when the camera is moving vertically, it loses the vertical edges. It always loses the edges that is parallel to its moving direction, which causes its
which causes the unstable texture. Like regardless of the event representation, that problem just exists because basically the sensor doesn't produce information, so we cannot compensate it using any post-processing method. So the question is, how can we utilize the advantage of event cameras while we want also keep the texture stable for some specific tasks? And for space types, the tasks we may not need it to perceive this static environment, but for other tasks, what if we want? So let's see how human beings tackle this problem. Well,
You won't hear the sound unless you shared it.
okay,
It's a share the sound down, and even that.
I'm gonna post. So yeah, I think many people are familiar with microsaccades. When we fix our gaze on static objects, our eyes is not completely still. It continuously stimulates the visual neuron by constantly jittering the eyeball. So microsaccades are believed to enhance the spatial details and prevent the image from fading. Now I have a simple demonstration.
We're supposed to fix our gaze on the red spot.
Yeah. And the next is on the red spot. After seconds, the bluish circle and the colorful background will just take away. That's because when we fix our gaze on the red spot, our microsaccades are suppressed. By the way, if the red spot is moving, you will see the perceptual fade is eliminated because of microsaccade. So let's demonstrate. So based on this is our design. So briefly, it enables the event camera to see the static boundaries.
Can you explain the
Yes.
the mechanics?
Yeah. It's in the next slide. So basically, we add a wedge prism. It will be detailed in the next slide. And when it rotates, just like moving the eyeball, we actively jittering events. And we can perceive the rotation using the encoder of the actuator, so that we can compensate the generated motion, so that we can get the very sharp edges.
And the angle of the wedge determines the how big is the circle on the focal plane. Does it depend on the lens focal length?
Yeah.
Or it depends, but how big is it typically in pixels?
Like as we test the 0.5 degree wedge prism, I can achieve a good balance between the event volume and the compensation accuracy.
But how much is that 0.5 degree?
Like 3 to 5 pixels, around 3 pixels.
The diameter.
The radius. Okay. Well, that's a detailed explanation about our mechanism, about the generation and compensation of the proposed work. So we have a wedge prism. It can deflect the light for a certain angle. And when it rotates, it just continuously deflects the incoming light to different pixels, so that we can actively jitter events. It rotates like this, and that's our raw output. When the camera is started, we can still perceive the background. And since we can compensate the rotation, we can get a very sharp edges as if there's no rotation.
Yes, it's video. It didn't look like it was continuously rotating, but some artifact of zoom. The zoom artifact, yeah. And what's the speed?
For the speed,
What's the frequency, I guess?
yeah, the 12.5 hertz. Why we also can achieve 20 hertz, but why we choose 12.5 hertz? Because in this case, every 30 seconds, milliseconds, we can perceive the half circle of the rotation, so that we compensate it. We can perceive all of the edges of all directions.
We usually accumulate frames over 33 milliseconds, and that's half a rotation.
Oh, 12.5 is half of 33.
So 33 milliseconds.
The calculation not
Yeah.
So we need to rotate for a certain angle to collect all the edges in different directions.
So right beside obviously.
Yeah, so a quarter circle is minimal, but sometimes it cannot be that perfect. So we so after the compensation, the output is just like the regular event camera. So we can use regular event camera processing algorithms to process this data. It's like a plugin. Oh, sorry, what's a question?
So what kind of applications do you envision using?
Yes, so in the next slides, we will introduce, we can improve the raw data quality of the event stream. And we applied one low-level vision task called corner detection and tracking, and also motion segmentation, and also a high-level vision task called human pose estimation. We'll discuss. I'll just later. So, in this experiment, we tested how our camera changes with data quality. So for the raw event stream, the standard event camera will have a phenomenon called a perceptual fading when it's changed its moving direction. But our camera just wouldn't. And as you can see here, there is the local density of each event. When the camera changes moving direction, there will be fewer events. And even if it can generate some events, if the events are very sparse, which contains less structural information, and we cannot visualize it. But for our camera, most our density are relatively high, so that we can utilize this dense data. And for another representation, event image, our system can be more informative, and it can generate more stable outputs. Also, for grayscale image reconstruction, when the camera is moving, we can achieve like similar performance as the standard event camera. But when the camera is static, the perceptual fading will happen, but our camera will stay stable. But since the network, we just use the off-the-shelf network, we didn't retrain or refine the network, so the performance looks not that good. So for low-level vision tasks, we applied on feature tracking and motion segmentation. For feature tracking, we want to show in some cases our camera can outperform both the event camera and this RGB camera. And for motion segmentation, we want to show that our system can preserve the advantage of event cameras in terms of high spatial resolution and the high HDR, high interaction. Yeah. So we did 4 sub-experiments.
What's the experiment? What's the experiment?
You have to track the first 3 experiments. We want to detect and track the corners. And for the last one, we want to segment the moving parts. The motion segmentation. We want to detect the high fast moving balls. The fast moving ball. So here, each red point, each detected corner is not detected in this frame, but detected and tracked for over 100 milliseconds. So in the simple cases, both our camera and the grayscale camera can achieve very robust performance, while the standard event camera will lose the track because of the perceptual fading. For complex environment, our camera is not as good as the grayscale camera, but still outperforms the standard event camera. Our camera is cool. And in the challenging illumination cases, both the grayscale camera and the standard event camera fails. The grayscale camera failed because of its low dynamic range, and the standard event camera failed because of its perceptual fading. And in this case, only our camera can have a robust performance. For the motion segmentation, the grayscale camera just cannot detect the ball causing too fast. But our camera and the standard event camera can robotically detect the fast moving object, meaning that our camera doesn't lose the advantage of event camera selection, but gives you stable texture as a bonus. So for high-level vision tasks, like human detection and pose estimation, let's just speak. For the human detection, our camera can reconstruct the image, grayscale image, in thousands of frames per second without the perceptual fading. And for pose estimation, our camera can even achieve 3,000 FPS with a clean image, clean texture. Also for future works, I think the main challenge is how to make the camera smaller. So one way is to utilize a smaller actuator in a mechanics way. So if we want maybe the optical image stabilization technology is helpful in this problem because it's small and lightweight, and most of these smartphones, they have this module. It's just a little optics module in front of the camera that can compensate for the camera motion to get a stable image. Maybe we can utilize it to generate events. However, currently shaking it in a very high frequency can cause many problems like heating and other things because the module is not designed for this case. And also it's hard to achieve circular motion because you can only shake it horizontally, vertically, or in a certain direction. And I think more promising direction may be from the optics and the material perspective. Can we adjust the applied voltage or something like that on a material or a small optical device that can change the optics properties of that material or change the direction of the incoming light? There are some possible ways, but I'm not an expert in optics, so I don't know. And also, if we can change the intensity instead of moving the pixel, although we will jitter the events on each pixel, maybe we can get something useful by observing the number of events jittered with each pixel or something. And if we for applications, for something discovered in class 6, it's not someone going to go with. So I think for that application, things with a kind of new hardware, we can do when we can explore many interesting things. For example, is the grayscale image reconstruction. Currently, as you can see, the quality is not that good and the motion is not compensated. But what if we can make the network learn the compensation parameters like the rotation, radius, and phase? Also, we can refine the network or an STM module in front of the network to learn the rotation, learn this rotation. Maybe we can get much better image reconstruction performance.
It's a little bit confusing to me. I don't see how you get 1,000 frames per second with a rotation rate of 12 hertz or whatever it is. That's independent, right? Yes. If you're rotating this, this circular orbit at 10 hertz or so, but you're still claiming that it gives you 1,000 frames per second in the video. Yeah, because if we just put the event stream, we'll choose the reconstruction network. Oh, this is by DNN that's reconstructed. Copy that. The copy that. Okay. Okay. Let's see. And obviously it exposes the DC features. Yes. Yeah. Well, so along these lines though, what would be the upper rate if you're doing 12 hertz rotation? How high in frequency can it reconstruct? It's still going to be good. I think it's independent from the rotation speed. But it's still time division multiplexing, right? So it's going to have temporal aliasing because you're still time division multiplexing somehow. Yeah, so because you're sampling different edges at different times. Yeah. So it is. Like I said, about this result of that, yes, our image can still get blurred. No, I'm not saying that. I'm just saying that it's going to alias because it is time division multiplexing. You're sampling different.
Yeah, it's Xinzong Wu.
Let's talk later. Yeah, I'll post my slides like right after the talk, and we can discuss.